All right, so welcome back. Let me recap really quickly. So, in the previous video, you were asked to solve the second order differential equation given some initial conditions. And we found the result, our proposed solution was y of t is equal to t. Now, that would mean y prime of t would be equal to 1, and y double prime of t would be equal to 0, right? So just to make sure you understand what you did, when you plug this information in, do you get a true statement? Well, you get 0 minus t equals negative t. You get a true statement. So there's your built-in check. Now, what I want to do is I want to practice simply using the table to reverse engineer the Laplace transformation. So for part A, for part B, what we're going to do is we got 2 over s cubed, 3 over s squared plus 9. I would very much encourage you to pause the video if you have the ability, but take a look at now starting with the right side and see which of these forms matches our 2 over s cubed or our 3 over s squared plus 9, and then see if you can grab the right information to reverse engineer to find f. Now, I'm assuming that you did not pause the video, but you could have. Maybe you did. Either way, let's go ahead and I'm not going to spend a lot of time going through this, but if you would have hunted through that table, you would have found the following. S to the n plus 1. That will work. That would work for this problem as long as n is equal to 2. And therefore, what you see is that since f of t is equal to t to the n, well, since we have reverse engineered it to figure out that n must be 2, then our f of t, our y of t, is equal to t squared. Okay, we're just practicing using reverse engineering this table. All right, now for this next one, we have 3 over s squared plus 9. And this, you won't find one that perfectly matches what we have here. At least I don't think so. Let me see. Maybe I'm incorrect about that. Yeah. So let me go ahead and get us started. Yeah, actually, I was lying. I was thinking we might have to do something with the 3 in the numerator, but nope, that's not with this one. So sine of bt was equal to b over s squared plus b squared. Now that fits the role, right? As long as b is equal to 3, then we can produce this f of s from this rule, right? So if b is equal to 3, you would have 3 here, and then 3 squared is 9. So that does match up perfectly. So b must indeed be 3. So now that we know that is the correct form, the f of t in this case is just sine of bt, with b being, and now b is equal to 3. So sine of bt, and there you go. So our answer is sine of 3t. Okay, so for this next one, I'm going to have to take a quick detour and make sure you recall a basically a pre-calculus topic, but you can see that this is not matching any of the forms of the Laplace transformations from table 7.1. So let me take a detour and I'll come back. So if you recall the idea of completing the square, then you can just fast forward. You can get back to the part where we solve it. But if you need a quick refresher, I'll try to go through this quickly. So first off, a perfect square trinomial is, so trinomial, meaning three terms, is one where when you factor, you get the same term twice. So see how this is x plus 2 times x plus 2, which you can write as x plus 2 squared. Now, if you were to FOIL this out, all right, if you were to FOIL this out, then you would get x squared plus 4x plus 4. And that's the idea, right? I mean, if you factor, you're going this way. If you FOIL, you're going the other way, right? However, so pretend that the game is that I erase this 4. Now I just have x squared plus 4x, right? So let's assume that if I just had x squared plus 4x, but I want to be able to write this as a perfect square trinomial, right? I want it to look like this. So now I understand that we know that all you would have to do is add 4, but the question, the completing the square part, is how would we determine what to add given the information in the problem, right? So how do we determine that it must be plus 4? Well, the little formula that you need is negative b cut in half squared. So the thing that you would need to add is negative b cut in half squared. That would allow you to write it as a perfect square trinomial. Now, so in this case, I think you'll agree with me that b is equal to 4. So if we were to plug that in, this would be negative 4 over 2 squared, which is just what? It's just negative 2 squared, which is 4, right? So that tells me exactly what to add so that I can write it in this form. FYI, the quadratic formula, just so if you want some more trivia in your life, if you were to take ax squared plus bx plus c equals 0 and complete its square, you would get the quadratic formula. Okay, so let me now try to apply that to our original problem. So in other words, take a look kind of down here, and you see how you see these, s minus a squared plus b squared. Let me see if I can show you how this is going to work. So we're going to have to rewrite this. So imagine that we have, so let's just start. We have s squared minus 2s plus 5. Now, as it stands, this is not a perfect square trinomial. Like, you can't write it in this form. So imagine that we're going to kind of scoot this 5 over for a second. So what we want to do is we want to add something here. So that we can complete the square. And that's no problem, right? Remember that in this case, b is going to be equal to -2. So if you were going to complete the square, it would be negative b over 2 squared. That would be negative 2 over 2 squared. Let me make sure I do my math right. So that ends up being 1 squared, yeah, equals 1. So you just figured out what to add in order to write as a perfect square trinomial. But look, you can't just, so pay attention here, you can't just plus 1 in this problem, right? You can't just, you would change the problem, but watch the manipulation here. So it's true, like you could plus 1 on this side if you plus 1 on this side, but even better, do you agree with me that if I add 1 and subtract 1 at the same time, that I've not changed anything? So in other words, I can plus 1 as long as I subtract 1 at the same time. Right? To add 1 and subtract 1, this is the equivalent of just adding 0. I've changed nothing. So now let's write the result. So now I would have s squared minus 2s plus 1. I don't know why I have 2 plus symbols. And that's going to be, so s squared minus 2s plus 1, and then 5 minus 1 is 4. So plus 4. Don't combine that 1 and the 4 yet. You'll be right back to where you started. Okay? So at this stage, we're going to think about it like this. And if you factor this trinomial, you would get s minus 1 squared. And of course, you can write 4 as 2 squared. Now, all of this work to rewrite this denominator. So now let's write the problem. So the new problem is, let's assume that your f of s is s minus 1 over s minus 1 squared plus 2 squared. Now, that very much resembles the form that we have here. Sorry, let me do, yeah, so you can see that that's starting to resemble the form. And I should be able to look at this and point out what is the A in this problem, what is the B. So I think you're with me that based on the form above, our A would be 1 and our B would be equal to 2. Now that's perfect, because now we can jump right to our answer. F of t is equal to e to the a t cosine of bt. And we already know what a is, we already know what b is. We just plug them in, and there's your result. So e to the t multiplied by cosine of 2t. Beautiful. Now, so that's the gist. That's the gist of these types of inverse transforms. And listen, this does get more complicated. So I don't want you to, although we might not venture that far, just for the sake of time. I don't want you to think that all Laplace transformations are easy because they already have all the answers. Let me tell you something. This is in the back of your book, and I do believe it's the very last page of your book, probably on the cover itself, the back cover. They'll have a whole list of common a table of Laplace transformations. There's much, much more than that. And sometimes it is an effort to find and manipulate to make it fit the right mold, okay? Sometimes you have to use like partial fraction decomposition and all of these things that I'm not going to ask of you. So as long as you feel good with these types of problems, you should be able to, for example, this here is example 2. You truly should pause the video and see if you can, let's see if you can actually determine this entire Laplace inverse. It would involve you trying to complete the square, etc. Obviously you don't have to pause the video. I just don't know how you get better at math unless you get in and like, you can watch me do math. It's like watching me play the piano, right? Like, how do you get better just watching? Like, you're deluding yourself, right? Like, at least I would be deluding myself. I would be operating under a false pretense of knowledge. I would think that my ability is greater than it really is. Now, if you pause the video and you go back and you try to use that table, which I'm going to grab in just a second. Right, so I'm telling you, well, you do whatever you want, but pause the video and try it, okay? If you don't have time now, then just pause the video and do it later. But pause the video and try it. Don't start with the solution, and don't start with me computing it for you, because it's not, well, it does help. I shouldn't say it doesn't help, but it's not as helpful. So if you can do this problem by yourself, that's a really good sign. But this is the last problem we're going to do. So if you don't, and how many times do I have to tell you? If you don't try this, then I don't have any more for you to try. Does that make sense? So, all right. So I'm going to go ahead and start writing the process of this solution. So actually, I tell you what, this is even better. I'm going to stop this video. That's how important I think it is for you to try this thing. I'm going to stop this video, and the next video is just going to be the result from this example, and that'll basically conclude conclude our study of Laplace transformations, I believe. If I'm wrong about that, then you will see some more videos.